Okay, guys, welcome back. Next up, we have Curtis Maloney. He spends a disproportionate portion of his time helping people on IRC to learn the joys of Django. So technically, he's a saint. No, sorry. Okay, guys, give it up for Curtis.
Right, so I'm going to be talking about AST. Anyone here know what ASTs are? Oh, even someone anticipated the question, well done. Anyone here ever played with Python's AST module? Because we all love Python and it lets us get to the insides. Also known as Funky Bob, as is mentioned, if you look me up on anything except Twitter, you'll find me there. I don't know who the Twitter Funky Bob is. I'd like to take a couple of minutes to talk about mental health. It's a bit of an issue for all of us, and it's a bit of something that traditionally people don't talk about. And I've found through my own experience and the experience of people I've talked with, talking about it makes it better. Not on its own, just talking about it, but talking about it with other people, you can experience that other people are going through the same thing, other people have ideas and solutions of how to deal with it, other people know solutions. Let's talk about this some more. And sometimes it's just a matter of asking someone, are you okay? Do you need a hug? Do you want to talk about it? That's it. That's all it takes. Not much. Blue Hackers is one particular organisation who have for many, many years now been supporting the fact that we're not just coders, we're people. There's plenty of other organisations. That's the first one I know of. If you are having trouble, do find someone to talk to. Most people are easier to talk to than you think. So what is AST? It is the abstract syntax tree. So when we're building a compiler, we take the source code and then it's broken down into tokens by Lexa, which then has to pass it off to a parser, which actually tries to make sense of each of those tokens. So the tokens would be things as little as this is a number, this is a string, this is an if, this is a new line. And then the parser will try and go, hey, you know what, you can't have if and then a number, and then a string. That doesn't make sense. So the parser is trying to put sense into it. And finally, the last stage is your code generation, which takes what the parser's done and turns it into something executable. Now, of course, modern, bigger compilers will have all kinds of fun stuff sitting around here, doing hundreds of thousands of optimizations and changes and whatever. We don't care about that. If you want to play with Python, the three best tools I've found to date for helping you play around with the AST. Of course, there's the Python AST module, which lets you get your hands on it and actually manually construct AST and deconstruct it and play around with it. Green Tree Snakes is actually, refers to itself as the lost documentation for Python's AST. Somebody has gone out of their way and written up several 100,000 words, I don't know, on how you can actually use AST yourself and what it all means, because the Python AST module documentation is actually quite sparse. It's not very useful. Without Green Tree Snakes, I wouldn't have been able to achieve what you see later on in the module. And AST, which is a fairly recent tool, takes all the stuff that's actually built into the AST module and wraps it up with some extra, much easier to use functionality, as well as full round trip, which means that you can take whatever your code is, turn it into AST, and then ask Astor to turn it back into Python source code. This is incredibly useful for debugging. What does AST look like? So here's a simple example of taking the Python AST module, asking it to parse a very, very simple bit of code, and this is what it comes out with. You can just ask AST to dump it into a string for you. So we've got a module because we've written effectively a Python code module, and the body of this module starts with a for element. The target of that for element in this case is a single item, which is a name, who's an ID of X, and the target context is we're going to store something into it. The iterator is something called Y that we're going to read from, and the body of our for loop is an expression that tries to call something called print. It has an argument called X. Whoops, wrong button. No keywords, no SR, and an or else case. Interesting differences. I mean, after a little while of playing around with AST, you can read that almost as easily as you can read your Python code. It's very easy to see from this the Python code that it came from. Some differences you notice about what we can say in Python that the AST actually doesn't represent. A good example is an if-else, if-elif. Elif does not exist in the AST. It simply creates nested ifs, which is sometimes worth remembering if you're going for really high-performance code. Of course, once we've done that, we can ask AST-Store to turn it back. So I take the same AST code that we were given and say to AST-Store, turn it into source, and that is exactly what it gives me back, which is pretty much exactly what I put in. But, you know, is that about all we can do? Well, no, of course not. Otherwise, this would be a very boring talk. We can manually construct our own AST, and I want to say I want to assign to something called x a value. I'm going to do a binary operation where the left value is a number and the operation is multiply and the right value is a number. I'll ask AST to turn this back, and of course that's what it gives me. Not exactly what I said, but definitely will do exactly what I said. There's a small point in working with AST. Python assumes that all the line numbers and positions have been set in your AST so that when everything blows up, it can tell you where you made a mistake. If you don't put those values in, you can't compile your AST. On the other hand, Python being Python and everything out of the box trying to make your life easier, hands you this thing called fix missing locations, where it just cascades the locations down from the top onto everything else so that you don't have to figure out how to do it and go through that tedium. Then you can use the normal Python compile statement. Anyone use this in their everyday life? Naughty. Might as well be using eval. You can specify the file name. There are different modes of execution to try and say, is this going to be command line execution? Am I pretending I'm on the command line interpreter, or is this in a module, or is this executing within a function? But most of the time you just use exec. So you get back this code object, which is actually a module. Now, in order to evaluate a module, you have to have a global context for it to work in, so we create a global scope, empty. Then we evaluate it, and we say, well, what did x come out to? There it is, 6 by 9. Well, we all know the answer is 42, but that's what we got. What can we do with this? What does this mean? Well, now we have a way that if we really take a little bit extra work, we can build Python code from source files that are not Python. Can anyone right now think of a great use for this? All right, we've got 3 people here. I know what you're thinking. Yep. Oh, turn C code into Python bytecode. That's an interesting one. You're a fucking masochist. But we can create little domain-specific languages. We can create little sandbox or macro languages. So say you want your users to be able to script up some aspect of your functionality, but of course, being sensible people, you don't trust them. They're crazy. They use your product after all. So you can give them a really, really limited thing and know exactly what it can access because you're generating the real code from it. Transpilers, like you were saying, we can go from one language to another language. Why not? Because we've got all the tools in place. Or a template language. Now, it may not be obvious, but I'm involved in the Django community. Have been a core team member for some months now. I've been using it for almost 10 years. And one of the big things we get told a lot is that Django's template language is slow. Yes, but it's doing a lot of work for you. But still, you know, why not? Let's have a really, really fast, bare metal, consenting adults form of template language where if you cut yourself, well, you knew there was a risk. We're not going to protect you, you're not hold your hand. So let's try and build something that will turn this, which looks very much like Django's template language, into this. So when I create an instance of it and then call this object, it will just iterate its root function, passing the context, and that will just yield all the things I've asked it to do. You'll notice here that the for loop is a little bit more complex than it needs to be. That was because I have not yet written the code to deal with local variables. This is a project I call Knight's Templater, because I'm an incorrigible punster. This mascot was designed by my wife, who does Cherry Jam. If you like the imagery, give it a look. So the first stage, as we said, you need a Lexa. You need something that is going to read that file in and turn it into usable tokens. This is our source file, and our Lexa is going to break it up something like this. So that's just a string literal, that's a variable expression, now we're back into a string literal, that's a block expression of some sort, that's another variable expression, there's actually a string literal hidden here because there's a space, another block. So we want to get something that will do this. Exactly as I was saying, text, variable, text, block, variable, text, block. Just chop it up into little pieces and tell you, this bit, I think it's a token of this type. How do you write one of these? Well, Django has one, but actually Django's is more complex than it needs to be, but it is very fast. This is my Lexa. First, we define a little bit of regex to say, well, this is how I recognize a block, this is how I recognize a variable, this is how I recognize a comment. Now, I'll just join that. I can match any of those. Then I have a generator here that will use the find ditter function in regular expressions, which as you iterate it, it'll find the next matching thing. Then we'll figure out where we've matched, figure out how many lines we've crossed since we got there, because we want to update our code. If we've jumped past where we were up to, there must have been a text token in between. So we will generate a text token from where we were up to where this token starts and set the line number on it. Then we'll move our pointer up of where we're up to. We'll get the name of the last matching group. So only one of these groups can possibly match at a time. So when you ask for the last group, that's the only group that matched. And then I can say, okay, create a token of that type. I just happen to have, I've used the enum module. I left out the enum from this because I couldn't fit it on the slide. With the content that we got, and let's tell it what line number we found it at. And then at the end, there may be some trailing text, so we'll put that out. That's how simple a Lexa can be. Obviously, if you have more complex tokens that may confuse each other and overlap and so on, that won't cut it. But there are tools like rply, which will make your life very easy in producing Lexas and parsers, as Marcus knows. Here's the start of my parser. All it does is consumes the nodes and tries to build structures out of it. So it's just going to start with the token stream that is generated from that token call. Okay, slides.com is really bad at aligning boxes. If it's a text token, then the code that we want to generate is pretty easy to follow. Yield a string whose value is the token content. If it's a variable, we're going to have to do a little more work. We're going to have to parse that expression and then yield something that is that expression that we've just generated. I'll get to that in a minute. And finally, if it's a block token, we're going to chop the name off the front. And then, okay, we have a condition where you may actually be scanning through, and like with for and end for, there's a case where you can say, I need to just collect all the tokens up until you reach this name. So that's the end node case. Finally, I'm going to look up my collection of tag processes and say, hey guys, I've got a tag of your type. Give me the code that I should be using. If it's not one of these, it's a comment and we throw it away because they're a waste of time, aren't they? If we've got no code out, there are certain cases where there's just nothing to say, then we just continue and keep going. If it's an instance of a yield or a yield from, we have to wrap it in an expression. That's just the way Python works. Finally, we set the line number on the node from the token so that we can actually, when we get errors, the line numbers in the error tracebacks will reference our template source code. And finally, we yield the node. Whoops, there we go. The next bit of the parser actually is called build method, and this is what calls that. So we had to have that root method, and in fact, when doing template blocks, that will also call build method to build other methods. So we call parse nodes until, which is simply a wrapper around parse nodes that passes at the end nodes and then remembers to chop off one of them because that won't be code. And we build our body of our code, which is simply a list of expressions. If nothing came out, if for instance we had an empty for block or an empty if block, we have to put something in there because an empty function just isn't allowed. So I just yield an empty string. Putting parse in would work too, but then that would confuse it because it wouldn't be a generator. Finally, we actually define a function. It has a name, bunch of arguments. This is a little wrapper I have to save myself from having to do things. Some of the AST things, when you're working with them, you have to explicitly put every single value that they define, and you have to put them all by name, although it looks like they're actually using named tuples inside. Put the body and the decorator, and that is our function, which is a method, and then we append it to our list of methods, which will then be used when constructing the class. I've forgotten what I'd written here. This is the bit that builds the class. It actually is quite simple. It just, yeah, I like indenting so I can remember where everything is. So we declare a class. We're going to call it template. Its body is all the methods we've just defined. Its base classes are either going to be the parent class if we were given one, or object, because anyone here not familiar with Django template languages and Ginger and other such, it's possible to do template inheritance, which works exactly like class inheritance. You simply say, I have this template, which is that one with these bits replaced. I do it using exactly that. Templates become classes, blocks in your template that can be replaced become methods, and so the inheriting class simply overrides the methods. But you have to be able to say what your parent template was. Then we have to append our call function. This is the code of the call function, and this is how you describe it in AST. So I'm going to define a function. It has arguments, self, and context. That's my own little wrapper again. It's a little more tedious to generate that. The body of the function returns a call to an attribute on a string. The attribute is called join. And the arguments to this call are a call to map, and its arguments are string and a call to. So, yeah, it gets a little nested, but so did all our parentheses up here. Some bits of this, I'm not going to write the parser myself because I have Python and it can do it just fine, thank you very much. So earlier I mentioned parse expression, and all I do is say to it, Python, parse this expression and turn it into AST for me. I'm not going to do that. I want variable expressions like this. Well, that's Python. I'll ask Python to turn it into code for me, and it will turn this into a bunch of keyword arguments and so on, which is where I use this, and pretend I'm calling a function, say to Python, parse that. I actually inject this portion of the token into the argument spot, and then say, parse that as if it's a call, and then I'm just going to get the arguments and keyword arguments that Python pulled out of there and hand them back. And that's already turned into AST for me. Why would I do the work myself when Python does it better? Also included in the AST module, and certainly improved upon in Astor, is the node visitor and node transformer classes, where you can hand it a big tree and say, go and visit every node on this tree, because I want to check for some of them and do some work on them. In this case, if we go back to this code, you'll notice that when the template says n, I actually look it up in the context. So I need some way to go through all my code and say every time somebody references a variable, I have to turn that from the normal variable reference into look it up in context, which is what this is doing. So this variable visitor is a node transformer, and I've said every time you visit a name, if it's in built-ins, I'm not going to touch it. If it's in my own little extra helpers or it's on self, I'm not going to touch it. Otherwise, I'm going to wrap the name in context, which just creates a subscript lookup on context, and the slice is an index whose value is the string, which is the name of whatever it was I was asked to do, and it's a load context. So that is effectively just context bracket name. So it's what turns these into that. It's a little difference, but it makes a big difference to your life. So whilst I was doing this, I was heavily focused on benchmarking because I figured, well, I'm doing this, it's going to be fast, I might see just how fast I am. So I found this. This guy produces a whole bunch of things under the Wheezy namespace, and all of them are focused only on speed. And as you get to looking at them, you'll realize that they've sacrificed usability for speed. That's my biggest issue with it. I added a module to it to use my template engine, and I changed the fourth one they had, which only tested his system and nobody else's, to be a fourth test that does the loop that's involved in this, but references inside the loop a variable that is defined outside the loop, or is not one of the loop variables. These are the various versions. Now, Ginger 2 uses markup safe, which has a C-compiled module for making HTML escaping much faster. And Wheezy HTML, which is used by Wheezy Template, has its own C module for doing exactly the same thing. So when they look really fast, part of the reason is they're using C. Everybody else is pure Python, as far as I can see. So this is what came out of the actual tests. Django is slow. All right, this is the number of milliseconds per test. It is an order of magnitude greater than anyone else. Ginger 2, often referred to, everyone looks at Ginger 2 to be the answer. And yeah, it's a lot faster, but I'm almost 3 times as fast as they are at doing this. Tension, I'd never heard of it before this, but they're doing pretty well. Tornado, not so good. Wheezy is blowing us out of the ballpark. It's just mind-blowingly fast. The total number of calls and the number of functions involved is an interesting way to get a metric on. Basically, every function call is expensive. You try to avoid it. This one breaks the template up and includes a bit more, and Django's just slowed down to half the speed. Ginger, well, yeah, they slowed down a lot. Not so much. Tension, yeah, they're out of the game now. Tornado is still fairly competitive, and Wheezy is just way down there. This is where it breaks the template up and has an extends, so that it's extending an existing template. And of course, Django is now way out of contention, being 20 seconds to render this template. Ginger is still pretty good, but now I'm 4.5 times the speed. Tornado is just edging in faster. And finally, this is referencing the outer loop, and it's pretty much the same story. Then we do the same thing, but there is a for loop in there with 10 items in the list. So in the initial one, Django's up to 32 seconds. I'm down at 2.6. Tornado, I'm beating them, but Wheezy's come up a bit. At this point, basically, it's all the same story, but as we go through the complexity, I start slowing down, everyone else starts slowing down, and it's a fight with Tornado. So I had a look to see how everyone else was actually doing their work. I do not understand how Ginger works. I haven't spent enough time on it, but I just started trying to figure it out and could not get my head into it. Tornado does almost exactly the same thing as Knights, but generates raw Python code and then just evals it. And that's why it's pretty much faster than I am in almost all cases because it doesn't have to do the context wrapping stuff that I do. Anyway, any questions? I think the microphone's coming. He jumped. He was first. Go on. Go on.
Yeah, Tornado, it basically just spits out pure Python code, so it doesn't transform the AST tree and it doesn't go down that route. So wouldn't that be a more viable approach for most of the use cases discussed?
Yes and no, because what I can do with what I've got here, and it was one of the avenues I haven't experimented with yet, is I can pass in a different class for it to base on and extend from that is not at all related to the template. And this is similar to what anyone, was it Cheetah templates way back in the day? Yeah. Used to be able to do, and you put your code into your templates and then the templates would render over top of that. Mostly this I did as an experiment just because I wanted to play with AST and see how fast I could make a template language. I get bored easily. They're viable options, and as you can see, the performance results are great. I just think also that they're going to run into problems of namespace issues. What if I happen to call one of my functions the same thing that you call your variable, and then everybody blows up?
Thanks for the talk and the renderer. Ginger takes one optimization that and automatically resolves constants when rendering the template and puts them instead of the context lookups in the AST. Have you looked into implementing that?
No, but I will after this. My next plan was actually to try and work on tracking local variables in things like for loops and so on. So if we have a look back on the code that I generated, I have this context scope, which is like Django's context. I've just gone and stacked a new layer of information, a new dictionary on top of the things to search for information. And then every iteration of the loop, I update it with all the iterator values from that loop. And that was the only way, the fastest solution I had for making sure that those values were put in the context and I didn't have to do any other magic. But I think I should be able to write a system for keeping track of what's in the local scope and then know not to look those up, which means modifying my this is hard to get through. Modifying the node visitor to keep track of it that way. But constants would be a much better option in some ways, yeah. At the moment, they're parsed by expression and so. Anyone else?
Hi, yes, thank you for the great talk. I just wanted to ask you about your thoughts on the practicalities of sandboxing using AST. So I see in this example here, you use ast.parse, ast.parse for one of your template codes, so you can't really, your templates need to be trusted. But if you had to make this so that an untrusted user could supply a template, how would you practically go about sandboxing it?
So this is actually my third attempt at a templating language going something along these paths, because I found a bunch of related tools as tokens, as tokenize and AST encode and all the rest of it. And one of the other approaches, which Marcus was helping me with, parses everything on its own, rather than using Django to do it at all, Python to do it at all. It does all the parsing and lexing and turning to AST of all the expressions, which is one way that you can keep yourself safe in that respect. When I was earlier talking about sandboxing, this is not an example. As I said, this is a consenting adults, sharp edges sort of, if you go and use this, you have to accept that you might shoot yourself in the foot in a really bad way. But if you were trying to build a sandboxed language for other people to use, you would build that syntax in a way that it wouldn't allow them access to the sort of things you don't want them to do, and then write your own parser in Lexa, and I'd recommend rply. It seems really good. Alex Gaynor recommended it to me, and he's on the PyPy team, so I figure he knows what he's talking about. Anyone else? Great.
Yeah, I've had a crazy idea for using the AST module for quite a while. As you know, I'm into monkey patching.
Really?
Yes. One of the problems with monkey patching is that because you are putting a wrapper object around another one that you want to call as you call through,
Well, I think I know where you're going with this.
that puts an overhead in. Now, the idea has been of if one can get the inner function object for a pure Python function anyway, take the bytecode off it, turn that into an AST, and then essentially take the...
Then inject your own code.
Yeah,
into
and basically instead of the wrapper having an extra call context around it, you can inject the code into the code of the inner one as a try finally, so that you can then do it before and after. Would that be practical, and could you see any problems with it?
As yet, I haven't seen anyone who's gone from bytecode up to AST. So basically, once you've got the compiled code, you have no chance there to get back. And it's not a one-to-one mapping. So I can't see how you'd go back from the code object into AST. Otherwise, you should be able to take that, wrap the body, no problem. As you see, exactly in this slide, I take existing AST and then wrap it up into something else. And you could just do that and wrap it in the body of a try except block. But that's going to be the trouble, getting back to the AST. If you have the source on hand, which of course is there, you could... Oh, okay. We'll talk later.
Okay, that's about all the time we have for questions. Sorry, if you want to see him after, I'm sure you can catch him at lunch.